A-Level Paper 1, Specimen Set 2. Let's look at this tricky question. 3.2. Use your knowledge of structure and bonding to explain why the melting point of iodine is low and why that of hydrogen iodide is very low. Tough question. First of all, you've got to know what iodine is. Iodine is in group 7, an atom in group 7. It wants to gain one electron. It can gain one electron by having two iodine atoms pair up in a 2I2. It is a small molecule. Once the two iodine atoms pair up in as a 2 with a covalent bond between them, they both gain an electron in each and have filled up their outer shell. It is small. It is molecular. Hydrogen iodide does the same. Hydrogen wants to gain an electron, iodine wants to gain an electron. They're also going to pair up in a small molecule. They're going to share a pair of electrons to form a covalent bond. That is also molecular, a small molecule. Okay. Small molecules bond with van der Waals bonds. They are weak bonds. Okay. So both of those molecules are going to have van der Waals forces of intermolecular attraction. Okay. Next, those intermolecular forces hold the molecules together, not within a molecule. They're covalent bonds between molecules. They're weak, so both iodine and hydrogen have melting points that are low because they're both molecular with van der Waals bonds. However, iodine is a bigger molecule. The atoms are bigger. Two big atoms, two big iodine atoms. Hydrogen is a small atom combined with iodine, I, so that's a smaller molecule. So iodine, I2, rather than HI, is a bigger molecule. So it's going to have more electrons. Okay. If it's got more electrons, it's got more van der Waals bonds, because a van der Waals bond is an attraction between the electrons in one molecule and the protons in the nucleus of another molecule. So it's going to have iodine, I2, because it's bigger, it's going to have more van der Waals bonds. More van der Waals bonds in total means stronger overall van der Waals bonding. That's going to need more energy to break than the weaker van der Waals bonds in hydrogen iodide. Hydrogen iodide for final mark. Hydrogen and iodine won't have the same electronegativity as iodine. In group 7 is going to have a slight delta minus. That will mean that the H will have a slight delta plus because the iodine will withdraw electrons towards itself. That's what an electronegative atom does, and it will get a slight delta plus compared to the hydrogen, which is not electronegative, and electrons will be withdrawn along the covalent bond away from it. So that's going to have slight polar bonding with slight delta plus, delta minus, but it's not as much of a factor as the larger number of van der Waals bonds in a large iodine molecule, and therefore iodine has a low melting point, but hydrogen iodide has a very low melting point because of the weaker, smaller number of van der Waals bonds. State why iodine does not conduct electricity. Things conduct electricity like metals or carbon, graphite, because they have delocalized electrons, and iodine doesn't have any delocalized electrons. Another shape of molecule. Draw the shape of molecule in IF3 and IF4 minus. So let's have a look. What's the central atom? I, because there's one of them. What group's it in? 7 electrons. In IF3, are we adding on any electrons on? Is it minus? Or taking any away because it's plus? No. So I've got iodine with 7 electrons in its outer shell. 3 F's come along and bond up 3 of the electrons. Therefore, there's 4 left over on the central iodine atom. They will form 2 pairs of electrons, two lone pairs of electrons. So the iodine has got 2 lone pairs and 3 bonded pairs. 2 add 3 is 5. When we draw it, it isn't flat. Okay. So, what do the two lone pairs do? Well, we know that lone pair repulsion is greater than lone pair bonded pair repulsion, which is greater than bonded pair repulsion, as all electron pairs repel equally. Okay. Therefore, the molecule is going to have its two lone pairs as far away as possible. One up, one down. When you get to the magical number of 5 bonds, 2 lone pairs, 2 bonded pairs and 3 lone pairs, 2 and 3 is 5. One pair always goes opposite from each other. One lone pair always goes opposite from the other to get as far away as possible. So I put them up and down. And the 3 Fs then are forced as far away from as possible from the 2 lone pairs in a planar shape. So even though the molecule is not planar when you draw it, the shape might still be planar when you describe it, because you don't describe the lone pairs. We're going to have a trigonal planar shape. Let's have a look at IF4 minus. Iodine group 7 electrons. It's the central atom because there's only one of those. 7 electrons, one more for the minus. It's got 8. 4 Fs come along, bond 4 of the electrons. There are 4 left over, 2 lone pairs. 2 lone pairs go up and down because we've hit the magical number of 5. The total number of bonds up and down, and the 4 Fs are then left in a minus, in a square planar shape, in the plane, in a square. Bond angle in IF3 is 120. You only describe the bond angle between the bonded pairs, and it's 90 degrees in a square planar shape, IF4 minus. Where do we put the minus? Easiest if you just put square brackets around it and a minus, because you don't quite know